Okay, so this is a key to go over the 1D motion problem set. So if you guys need help with any of these problems and we're having a hard time with it, this is your place to turn. So I'm going to go over all of these in this problem set, and I'm going to go over them here in this Jamboard, and you can access these as always from the quarter agenda. There are the notes right here under today's date. So these are the two equations to describe the position and velocity of an object accelerating in one dimension. So our first one is the velocity at any given time is equal to the acceleration times the amount of time that's passed plus the initial velocity, right? So the velocity at this time is equal to acceleration times that time plus the initial velocity. So that's our one equation. The second equation is the position at any given time is equal to 1/2 the acceleration times the time squared plus the initial velocity times the time plus the initial position. Other note down here is that if the acceleration is 0, then this equation right here becomes this, right? It simplifies to the position is equal to the velocity times time plus the starting position. If you need any reminder as to what any of these terms are in these equations, you can, as of course, always go back to the notes that we talked about previously. So with that being said, let's go ahead and get started. So this first problem, we've got this plane that's taking off from rest at the end of a runway with an acceleration of 4 meters per second per second. 8 seconds later, the plane's moving fast enough to generate the lift required to take off. So one thing I like to do for these problems generally is I like to record the information that we know. So we see right here the starting position was 0 meters. I'm going to make this bigger real fast. There we go. So the starting position is 0 meters, right? We know the acceleration is 4 meters per second per second. And the time that we're concerned with is 8 seconds. Right, so after 8 seconds have passed, we want to know where on, in this case, we want to know where on the runway the plane took off. But this is what we know, right? So this is the base information that we're given: starting position, its acceleration, and the time. We also happen to know, right, it takes off from rest. So we know the initial velocity is 0 meters per second. That is also important to know. So VI is 0 meters per second. Okay. So where on the runway does the plane take off? That where tells us that we're looking for a position. So we're going to go ahead and use our position equation, which is the position is equal to 1/2 the acceleration times time squared plus the initial velocity times time plus the starting position. All right, so let's go ahead and plug in these numbers that we happen to know. We don't know the position, but we do know the acceleration, which is 4. And we know the time as after 8 seconds is when it takes off. So we'll plug in 8 seconds for the time, and we want to make sure that we square that. Now keep in mind, right, this is only squaring this part, right? It's only squaring the time. It's not squaring the whole thing. And then we're going to add that to the initial velocity, which happened to be, since it was at rest, the initial velocity was 0. We multiply that by the time as well, which was 8 seconds. 0 times 8 is, of course, going to be 8, and the initial position was also 0 meters, right? So this part here ends up becoming 0. This is already 0, so we're really just left with the position is equal to 1/2 the acceleration times the time squared. So I can actually start filling that in. So let's see. So 1/2 of 4 is 2. So that simplifies down, and then 8 squared becomes 64 seconds squared. Right? So we have 64 seconds squared, and so 2 times 64, we plug that out, and the position should be, if my math is correct, 128 meters. So that is the position on the runway where the plane finally takes off. All right, moving on to the next problem. So in this case, right, we want to know how fast is the plane moving at takeoff. Well, once again, we know the acceleration is 4 meters per second per second. The starting position is 0 meters. The initial velocity is 0 meters per second. And the time of takeoff, the time that we're concerned with, is 8 seconds, right? So if we don't know how fast, there we're working with velocity. So we're going to use our velocity equation. So the velocity is equal to the acceleration times the time plus the initial velocity. Okay, and we can go ahead and plug in the information that we know. We want to know the velocity, we know the initial velocity, we know the acceleration, we know the time. So the velocity is equal to 4 meters per second times 8 seconds plus the initial velocity, which was 0 meters per second. Right? So the velocity should end up being, if I'm wrong with that, 32 meters per second. Right? And there you go. Bada bing, bada boom. So there we have that. Let me check the math on this real fast. I grabbed my calculator. I'd hate to lead you guys astray. Yep, that appears to check out. So there we go. So now we know the information for what its position is when it took off and how fast it was moving when it took off. And this is for a simple object that is speeding up to the right, starting in a position of 0. So this one's pretty straightforward, very similar to our fan cart, pretty easy to solve for. This last piece is we want to sketch the position and velocity graphs for the plane. Right, so if I have my position over time graph, and I have my velocity over time graph, if I were to sketch the position of the plane through time, I know its starting position. It is important to record those. So its starting position we said was 0 meters. Its initial velocity was 0 meters per second. Its acceleration we don't actually need to know for this, and the time we can kind of know, but we don't necessarily need to know. We'll just say out here is about 8 seconds towards the end. So its starting position is 0, so we know that, right? And its position was increasing in the right, moving to the right, so in the positive direction, and it was speeding up, meaning that the slope is going to be getting steeper. So the slope's going to start flat, and then it's going to get steeper as time goes on, right? So that would be the position time graph for this. And the velocity time graph, its velocity starts at 0, right? And it's going to be increasing its velocity through time. So this is going to be, but it's going to be increasing at a steady rate, a constant acceleration. So it's just going to be a straight line, something like, let me try and draw that a little straighter. Something like that, right? So just like our fan cart for this case, pretty straightforward. Now in the second problem, here we've got a plane that is coming down for landing, so it's moving this way, still moving to the right, and it's touching down for landing 10 meters from the end of the runway with a speed of 40 meters per second, and comes to rest 5 seconds later. Right? So in this case, its initial position that we're concerned with is actually 10 meters, right? That's the point where it first touches down. Its initial velocity we're given is 40 meters per second is when it touches down. And the time of concern is 5 seconds. All right. And let's see, and it comes to rest 5 seconds later. So its final velocity is 0 meters per second, right? So after 5 seconds, its velocity is 0 meters per second. So if we want to know the acceleration of the airplane, right, there's two equations that we can use. We could use, because both of them contain acceleration, so we could use the velocity is equal to acceleration times time plus the initial velocity, right? We could use the position is equal to 1/2 the acceleration times time squared plus the initial velocity times time plus the starting position, right? So, and you can think of this as its position at any point in time, or in this case it would be its final position, and this would be its final velocity, or its velocity after those 5 seconds. So looking at this, if we look at this one, we don't know its final position, we don't know the acceleration, we do know the time it took, we know its initial velocity, and we know the starting position, but because we have two unknowns, right, we can't use this one. Okay, so we're not going to use this guy. We're instead going to use this guy, because if we look at this, we know the final velocity comes to a stop, so 0 meters per second. We know the amount of time it took, which is 5 seconds. And we know the initial velocity, which was 40 meters per second. Right? So we should be able to find what the acceleration is. So let's use that, and we'll say the final velocity is 0 meters per second is equal to the acceleration times 5 seconds plus the initial velocity, which is 40 meters per second. Well, here we're going to go ahead and subtract 40 meters per second from each side to isolate these multiplied variables. So we're going to subtract 40 meters per second, and we end up with negative 40 meters per second is equal to acceleration times 5 seconds. So we're going to divide both sides by 5 seconds. And that gives us then the acceleration is equal to negative 40 divided by 5, which should be negative 8 meters per second per second. So that was its acceleration. Now, what does this mean? Right, what does that negative sign mean? Well, what that means is the negative sign means acceleration, and therefore F net was to the left, right? So the negative indicates the direction here. In this case, the negative direction is the left direction. So that means that the net force was to the left. So this plane was moving to the right, but experiencing net force, experiencing an acceleration to the left. So it's moving to the right, net force to the left. So that means it's going to be moving to the right and slowing down, right? Because the net force is acting opposite the direction of motion. So that's the first part. Now for the second part, we want to know where on the runway did the plane come to rest. Well, now we know the acceleration was negative 8 meters per second per second. We know the initial position was 10 meters. We know the initial velocity was 40 meters per second. And we know the time that it took to come to a stop was 5 seconds. And we know that the velocity final, just throw in there, although we don't need this for this, was 0 meters per second. So now we want to know where on the runway. So we're talking about position. So the position is equal to 1/2 the acceleration times the time squared plus the initial velocity times the time plus the initial position. So let's plug in what we know. So the position that it ends up at is equal to 1/2 acceleration, which is negative 8 meters per second, times our time, which is 5 seconds, squared. And once again, that is only right for the 5 seconds, plus the initial velocity, which was 40 meters per second, times the time, which is 5 seconds, plus the starting position, which was 10 meters down the runway. So let's see, we can do some math here. 5 squared, this becomes 25. So, and half of negative 8 is negative 4. So negative 4 times 25 seconds squared, plus 40 times 5, that should be 200 meters, plus 10 meters, right? You should notice if we have meters on top and seconds on the bottom, and we multiply it by seconds, we got meters per second times seconds. You'll notice the seconds on top and bottom cancel. That's an important thing to make note of, so we're left with just meters. That's how I know that this would be 200 meters. So I calculate that. And so here we get negative 4 times 25. That would be negative 100. That is also going to end up being meters, right? Because meters per second squared times, so we have meters per second squared is another way of writing meters per second, times seconds squared, and those cancel as well. So we're left with just meters once again. So I've got negative 100 meters plus 200 meters plus 10 meters. That means that my final position should be 200 meters, should be 110 meters down the runway. That's where it finally comes to a stop. Now, does that make sense? Just kind of doing a common sense check? Yeah, it makes sense. It, relatively speaking, at least we're not getting something within here and here. We're getting something a little ways down. So it traveled an additional 100 meters after touching down there. And that's what the acceleration that had, taking 5 seconds to stop with an acceleration of negative 8 meters per second per second. Right? So that's how we would do number 2. And then the last part is, of course, the position and velocity graphs. Right? So if we have our position over time and our velocity over time. Right, once again, noting it's important to note here the initial position, which was 10. Right, noting the acceleration was negative 8. The initial velocity was 40. And the final velocity was 0. So the velocity after those 5 seconds, time was 5 seconds. And let's see what else. We now know the final position, which was 110 meters. Right. So if we look at the position over time, well, it went from 10 meters to 110 meters. Right. But it was slowing down. Right. So it's still moving to the right. It's still moving this direction, starting at 10 meters. Right. But then it was slowing down as it got to 110 meters. So this one would look something like this, starting out fast and slowing down, right? So something like that would be the position time graph. Meanwhile, the velocity time graph, the initial velocity was actually 40 meters per second, right? So this would be 40 meters per second. Up high, and its final velocity is 0 meters per second, and that took about 5 seconds. So, and the acceleration was constant, so it's going to have a constant negative slope indicating a negative acceleration, which would look like that. So, and hopefully you guys remember that from what we talked about last week with position and velocity graphs. Hopefully that rings pretty good of a bell. And then problem number 3. So here we've got a football player who's starting from the 10-yard line and runs in the positive direction in a straight line at a constant speed of 18 miles per hour for 3.5 seconds before being tackled. And we want to know where on the field is the player, right? So if we want to know where on the field is the player, we're talking about position. Right, so we're talking position is equal to 1/2 the acceleration times the time squared plus the initial velocity times the time plus the starting position. Whew. And let's see what we know. So it starts from the 10-yard line or the 9.1 meter line. So the initial position is 9.1 meters. Right? And they run in the positive direction, that's to the right. It means that their velocity is going to be positive in a straight line at a constant speed of 18 miles per hour or 8 meters per second. So the initial velocity is 8 meters per second. And the time that they're running is 3.5 seconds, right, before being tackled. Now, they run a straight line at a constant speed. What that constant speed means is that the acceleration is going to be 0. Right, their speed is not changing, their velocity is not changing, so the acceleration is 0. So we can also plug that in. Our acceleration is 0 meters per second per second. So let's plug these in. Position is equal to 1/2 times 0 times 3.5 squared, second squared, plus the initial velocity, which was the velocity the whole time, which is 8 meters per second, times the amount of time, which is 3.5 seconds, plus the starting position, which was 9.1 meters. Okay, this whole part here, since we're multiplying by 0, this whole part cancels to 0. So then I get the position is equal to 8 times 3.5, which is 28, plus 9.1 meters. So that brings us to a final position of 37.1 meters down the field. There you go. So that's where the player is on the field, right? I would say, just generally speaking, that seems like a pretty good gain going from, this would be about the 40-yard line, so about the 10-yard to the 40-yard line. So that's about a 30-yard gain. It's pretty solid, right? And so in this case, now the last thing to do is sketch the position and velocity graphs for the player. In this case, the velocity is constant, right? So the velocity is constant the whole time at 8 meters per second. Acceleration is 0. the initial position is 9.1 meters, right? And the final position is, what did we say that was? 37.1 meters. Okay, so the starting position is about 9.1 meters, so starting about here. And the final position is about 37.1 meters. So that's up there. And they're running at a constant speed in the positive direction to the right. So this is going to be constant speed means that the slope is going to be straight, right? Just something like that. And for the velocity, meanwhile, the velocity is staying at about 8 meters per second the whole time. So their velocity is just a nice straight flat line. So I should have drawn those with black lines to keep things consistent. So we go, and here we're at like about 8 meters per second. So you're at 8 meters per second. And of course, once they're tackled, this would drop immediately to 0. But that is the idea. So hopefully you guys were able to try and get through those on your own. If you guys need help, I hope that this video key helped and that you guys feel relatively comfortable trying these on your own, because we will be doing some more of these in the coming week.